What if everything we think we know about the universe is just the surface of something far stranger? Picture the night sky, those countless stars, galaxies stretching beyond sight. It feels immense, yet astronomers estimate we've only mapped about 4% of the cosmos, the rest a haunting mystery cloaked in darkness. But what if that darkness isn't empty? What if hidden within it are structures so bizarre, so unlike anything we've seen, that they rewrite the rules of reality itself? From cosmic strings thinner than an atom yet stretching across the universe, to shadow dimensions brushing against our own, there are theories that dare to suggest the fabric of existence is far weirder than we ever imagined. For centuries, we've gazed upward, believing the universe to be a vast but orderly place. Yet the deeper we look, the more it feels like peering into a mirror maze. Take dark matter, for example, an invisible force holding galaxies together, yet utterly silent, leaving no trace except its gravitational pull. Or dark energy, that mysterious pressure tearing the cosmos apart at an ever-increasing speed. These aren't just gaps in our knowledge, they're clues, hints that the universe might be built on foundations we're only beginning to glimpse, and that's where things get thrilling. Because when scientists confront the unknown, they don't just shrug, they dream, they theorize, they imagine possibilities that sound like science fiction, yet could be the keys to unlocking the universe's deepest secrets. That's exactly what we're diving into today. 30 of the most mind-bending theories about the hidden structures of reality. Some are elegant, weaving space and time into intricate patterns. Others are almost unsettling, proposing layers of existence beyond our perception. But all of them share one thing: they challenge us to think bigger, to question the very nature of what's real. So if you've ever wondered what might lie beyond the edges of our understanding, or felt that tug of curiosity when staring at the stars, you're in the right place. This isn't just a list, it's an expedition, and by the end, you might never see the universe the same way again. One of the most fascinating ideas lurking in the shadows of cosmology is the existence of cosmic strings, threads of pure energy thinner than a proton yet stretching across the entire universe. Think of them as cracks in space-time itself, frozen remnants from the first moments after the Big Bang, when the fabric of reality was still settling into its current form. These aren't physical strings you could touch or see, but one-dimensional flaws in the structure of the cosmos, like wrinkles in a sheet that never smoothed out. Their density is almost unimaginable. A single inch of cosmic string could outweigh an entire mountain, warping space around it with a gravitational pull so intense it could bend light or even distort time. What makes cosmic strings so compelling isn't just their bizarre nature, but the clues they might leave behind. Some scientists speculate these filaments could have acted as cosmic scaffolding in the early universe, guiding the formation of galaxies by creating dense gravitational wells where matter pooled together. Others suggest they might leave faint but detectable fingerprints in the cosmic microwave background, the afterglow of the Big Bang, as subtle temperature variations or strange, linear patterns in the radiation bathing our universe. There's even a wilder possibility. If two cosmic strings crossed or snapped, they could send ripples through space-time itself, producing gravitational waves we might one day detect. Yet for all their theoretical grandeur, cosmic strings remain elusive. No direct evidence has confirmed their existence, but their potential impact is too significant to ignore. They embody a thrilling truth about cosmology. The universe's hidden layers often defy intuition, revealing a reality far stranger than our everyday experience suggests. And if we ever do find proof of these space-time cracks, it wouldn't just solve a mystery, it would rewrite our understanding of how everything, from galaxies to the laws of physics, came to be. But if cosmic strings are the universe's cracks, then dark matter filaments are its hidden scaffolding, a vast, invisible web weaving galaxies together in a structure so immense it defies comprehension. Imagine the cosmos not as scattered islands of light, but as an intricate network with threads of dark matter stretching billions of light years, connecting galaxy clusters like beads on a string. These filaments aren't just theoretical, they're the backbone of the universe's large-scale structure, dictating where galaxies form and how they move. And though we can't see them directly, their gravitational fingerprints are everywhere. Take the Millennium Run, one of the most ambitious supercomputer simulations ever created. When scientists fed the laws of physics into this digital universe, dark matter didn't spread evenly. It clumped into an intricate cosmic web, with dense nodes where galaxies clustered and faint tendrils bridging the gaps between them. The eerie part, this simulated web matched the real distribution of galaxies we observe in the night sky, as if the universe itself were following a blueprint written in invisible ink. But how do you map something you can't see? Gravitational lensing offers a clue. When light from distant galaxies passes near these massive filaments, it bends, like a straw seeming to warp in a glass of water. By studying these subtle distortions, astronomers have begun tracing the outlines of the cosmic web, revealing faint streaks of dark matter threading through the void. Some experiments, like the Dark Energy Survey, have even captured hints of filamentary structures stretching between galaxy clusters, their gravity subtly tugging at the fabric of spacetime. Yet the deeper mystery remains. What is dark matter? Is it a sea of undiscovered particles or something even stranger? Whatever the answer, these filaments are more than cosmic architecture. They're a reminder that the universe's grand design is written in a language we're still learning to read. And with every new observation, we're one step closer to deciphering it. Now imagine if everything around us, the stars, planets, even the air you're breathing, wasn't truly three-dimensional at all, but a kind of cosmic illusion. That's the jaw-dropping premise of the holographic principle, a theory so radical it turns our understanding of reality inside out. Picture a movie projected onto a screen. The images appear to have depth, movement, even life, yet they're all encoded on a flat surface. The holographic principle suggests our universe might work the same way, with all the information about space, time, and matter somehow stored on a distant, two-dimensional boundary, like a shadow cast from the edge of existence. This bizarre idea didn't come from nowhere. It grew out of a paradox swirling around black holes, those cosmic traps where gravity is so strong even light can't escape. In the 1970s, physicist Stephen Hawking made a startling discovery. Black holes aren't completely black. They slowly leak radiation, fading over time like a dying ember. But this raised a terrifying question: what happens to all the information about the objects the black holes swallowed? According to quantum mechanics, information can't truly be destroyed, yet Hawking's math suggested it was vanishing forever. The conflict became known as the black hole information paradox, and it threatened to unravel our understanding of physics. Then came Leonard Susskind and his colleagues, armed with an elegant solution. They proposed that the information wasn't lost, it was preserved, encoded on the black hole's event horizon, the point of no return. Think of it like a celestial thumb drive, storing every detail about the doomed objects in tiny, two-dimensional pixels. But here's where it gets wild. If this was true for black holes, could the entire universe operate the same way? The holographic principle boldly extends this idea, suggesting that the three-dimensional world we experience might just be a projection from a flat, distant surface we can't see, a cosmic hologram. The implications are staggering. If the holographic principle is correct, space-time itself might not be fundamental, but emergent, like the surface of a pond emerging from countless rippling water molecules. This could reshape everything from how we understand gravity to the nature of quantum mechanics. Even more mind-bending, there might be ways to test it. Some scientists are hunting for holographic noise, tiny, jittery fluctuations in spacetime itself that could betray its pixelated, two-dimensional origins. Others are probing the cosmic microwave background for faint statistical patterns that might match holographic predictions. Yet whether the principle holds or not, its brilliance lies in the questions it forces us to ask. How deep does reality truly go? Are we living in a universe or on its surface like characters in a painting who mistake their canvas for a world? The holographic principle doesn't just challenge our assumptions, it invites us to wonder if we've been reading the cosmos all wrong, mistaking the projection for the screen. And that's a mystery worth unraveling. What if our universe isn't the only one, but just one bubble in a vast cosmic froth of realities, each with its own rules? This is the startling vision of the inflationary multiverse theory, where the fabric of existence isn't a single expanse but an ever-expanding sea of universe bubbles, each born from the same primordial chaos but evolving into wildly different realms. Picture a pot of boiling water bubbles constantly forming, colliding, popping, but instead of steam, these bubbles contain entire universes, some with laws of physics unlike anything we've ever seen. The roots of this idea stretch back to cosmic inflation, the theory that our universe underwent a mind-boggling expansion in the first sliver of a second after the Big Bang. But what if that inflation never truly stopped? Eternal inflation suggests that while our universe settled into its current state, other regions of spacetime kept stretching exponentially, birthing new universes in an endless cascade. In this view, the multiverse isn't static. It's a living, bubbling foam where new realities constantly emerge, each with its own unique physics. Some might have stronger gravity, making stars burn out in moments. Others could lack electromagnetism entirely, leaving matter formless and dark. The real twist, these bubbles might not stay isolated. Theoretical models suggest they could collide, leaving scars in the cosmic microwave background like bruises on spacetime itself. Astronomers have even searched for these signatures, scanning the afterglow of the Big Bang for odd, circular patterns that might betray a primordial clash of universes. While none have been confirmed, the possibility lingers. Our universe might bear the fingerprints of a long-ago encounter with another reality. This theory also offers a tantalizing answer to one of cosmology's biggest puzzles. Why does our universe seem so finely tuned for life? If gravity were slightly stronger, stars would collapse too quickly. If weaker, they'd never ignite at all. The multiverse sidesteps the need for a designer by proposing a simpler explanation. In an infinite sea of possibilities, some bubbles will inevitably have the right conditions for life purely by chance. We're not in a special universe, we're just in one of the few where asking these questions is even possible. Yet the multiverse isn't without controversy. Some argue it's untestable, more philosophy than science. Others counter that indirect evidence, like bubble collision signatures or anomalies in fundamental constants, could one day lend it weight. Whether proven or not, this theory forces us to confront a humbling truth. Our cosmic home might be stranger than we ever dreamed, just one page in an endless library of realities, each telling its own version of existence. And that's enough to make anyone wonder, what stories do the other bubbles hold? At the smallest scales imaginable, where distance and time lose their familiar meaning, spacetime itself might not be smooth and continuous, but a boiling, turbulent ocean of pure chaos. This is the mind-bending world of quantum foam, a theory suggesting that the very fabric of reality is riddled with tiny, frothy bubbles popping in and out of existence, like a cosmic version of soap suds churning at the speed of light. Picture the surface of a stormy sea, where waves crash and swirl unpredictably, except here, the waves are fluctuations in spacetime itself, vanishing as quickly as they appear. These aren't just mathematical quirks. According to quantum mechanics, empty space is never truly empty. Particles and antiparticles flicker into being constantly, borrowing energy from the universe in fleeting bursts before annihilating each other. But at the Planck scale, a distance so small it's a trillion times tinier than an atom, this chaos might warp spacetime itself into a labyrinth of microscopic tunnels, loops, and voids, constantly reshaping the stage upon which reality plays out. The idea traces back to physicist John Wheeler, who envisioned spacetime not as a static stage but as a dynamic, almost living thing. He theorized that at these unimaginably tiny scales, spacetime could twist itself into temporary knots of pure energy called JWST, short for gravitational electromagnetic entities. These wouldn't be particles in the traditional sense, but ripples in the geometry of spacetime so intense they could briefly mimic the behavior of matter. Imagine a whirlpool in a river. The water isn't an object, but its motion creates a structure that behaves like one. JWST could be spacetime's whirlpools, appearing and dissolving so quickly we'd never notice, yet their existence would mean that energy and geometry are far more intertwined than we ever realized. But if quantum foam is real, why can't we see it? The problem is scale. Probing spacetime at the Planck level would require energies trillions of times greater than what our most powerful particle colliders can produce. It's like trying to study the grooves on a vinyl record with a sledgehammer. The tools we have are too blunt for the task. Even indirect evidence is elusive. Some theories suggest that if spacetime is frothy, light traveling vast cosmic distances might pick up subtle distortions, like a shimmer in starlight caused by the foam's turbulence. Experiments have hunted for these effects, but so far the quantum foam remains hidden, its existence lingering just beyond the edge of proof, yet the implications are profound. If spacetime is fundamentally foamy, it challenges Einstein's vision of a smooth, continuous universe, suggesting instead a realm where reality itself is pixelated, fluctuating, and inherently uncertain. It could even reshape our understanding of black holes, the Big Bang, and the nature of gravity itself. Quantum foam doesn't just hint at a hidden layer of reality. It whispers that the universe might be far wilder, far more restless than we ever dared to dream. And that's a mystery worth diving into, no matter how deep the foam may churn. What if the Big Bang wasn't the beginning, but just the latest chapter in an endless cosmic cycle? Enter the ekpyrotic universe, a theory so radical it replaces the singularity of the Big Bang with a collision between two higher dimensional worlds. Picture our universe as a sheet of paper floating in a vast, unseen space. Now imagine another sheet drifting toward it. When they meet, the impact unleashes enough energy to birth stars, galaxies, and everything we know. This isn't destruction, it's creation, a fiery rebirth from the ashes of a previous cosmos. The name ekpyrotic comes from an ancient Greek word meaning conflagration, and it's easy to see why. In this model, our universe exists on a three-dimensional membrane, or brain for short, floating in a higher dimensional space. Another brain lurks nearby, invisible to us but bound by the same hidden dimensions. Every few trillion years, gravity pulls them together. The collision doesn't happen in the way we'd expect, no dramatic explosion in space. Instead, the energy of the impact floods through the brains, sparking a rapid expansion we perceive as the Big Bang. The universe isn't born from a single point of infinite density, but from a smoother, more distributed event. This idea tackles one of the Big Bang's biggest puzzles. Why does the cosmic microwave background, the afterglow of creation, look so uniform? Inflation theory solves this by proposing a fleeting period of hyperexpansion, smoothing out wrinkles in spacetime. But the ekpyrotic universe offers an elegant alternative. As the brains draw closer, their gravitational interactions stretch and flatten any irregularities, like rolling out dough before baking. By the time they collide, the stage is set for a perfectly even universe. No need for inflation, just the natural consequence of higher dimensional physics. But the real magic lies in what comes next. Unlike the Big Bang's one-time event, the ekpyrotic model suggests an eternal cycle. After the collision, the brains rebound, drifting apart and gathering energy until gravity pulls them back for another cosmic rebirth. Time becomes a loop, with each iteration subtly different from the last. Some versions of the theory even propose that dark energy, the the mysterious force accelerating the universe's expansion, is a sign the brains are already beginning their slow dance toward the next collision. Of course, this raises questions. If the brains exist beyond our perception, how could we ever detect them? Some physicists suggest hunting for gravitational waves from the last collision, ripples in space-time that would carry a distinct signature unlike those from black holes or neutron stars. Others look for imprints in the distribution of galaxies, searching for patterns that inflation can't explain. So far, no smoking gun has emerged, but the ekpyrotic universe remains a compelling alternative, challenging us to rethink not just how the universe began, but whether beginnings and endings are even the right words at all. It's a humbling thought. Our entire cosmic history might just be one act in an infinite play, with dimensions we can't see and forces we've yet to name pulling the strings. Whether the ekpyrotic universe is real or not, it reminds us that the deepest mysteries of existence often lie just beyond the edge of our imagination, waiting for the next collision of ideas to bring them into view. Forget the idea of a universe spread evenly like butter on toast. What if it's more like a tangled root system, repeating the same intricate patterns whether you zoom in or out? This is the provocative heart of fractal cosmology, a theory that throws out the cosmological principle, the long-held belief that the universe looks roughly the same everywhere when viewed at large enough scales. Instead, it suggests the cosmos is built like a fractal, with galaxies clustering in self-similar ways whether you're observing a local group or the entire observable universe. Imagine a snowflake's branching arms, each tiny segment mirroring the whole structure. Now picture that on a cosmic scale, with filaments of galaxies twisting into spirals that echo themselves across billions of light years. The idea didn't emerge from pure speculation. Astronomers began noticing oddities in galaxy surveys decades ago. When they mapped the universe's large-scale structure, they expected to find a smooth, random distribution like sprinkles evenly mixed into cake batter. Instead, they found clumps within clumps, voids within voids, with no clear cutoff where the lumpiness faded into homogeneity. Some studies, like the Sloan Digital Sky Survey, even revealed galaxy clusters arranged in vast, ring-like formations spanning hundreds of millions of light years, structures so colossal they shouldn't exist if the universe were truly uniform at large scales. Proponents of fractal cosmology, like physicist Luciano Pietranero, argue these aren't anomalies but evidence of a deeper pattern. In their view, the universe follows a fractal dimension, a mathematical measure of how completely a structure fills space. A straight line has a dimension of 1, a flat plane 2, but a fractal might have a dimension like 2.3, meaning it's neither purely flat nor fully voluminous. Apply this to the cosmos, and you get a universe where matter isn't evenly distributed but organized in a complex, repeating hierarchy. It's as if the universe has a hidden blueprint with galaxies clustering into groups, those groups forming superclusters, and superclusters weaving into even larger threads, all obeying the same underlying fractal rule. Critics, however, aren't convinced. They point to measurements of the cosmic microwave background, which show a remarkably even distribution of temperature fluctuations, exactly what you'd expect if the early universe were smooth. If fractal patterns existed at all scales, they argue, these primordial ripples would reflect that imbalance. Some concede there might be fractal-like behavior up to a certain scale, but insist homogeneity must win out eventually. The debate hinges on a tantalizing question. Are we seeing genuine fractal structure, or just the universe's messy adolescence still settling into equilibrium? Yet the implications of fractal cosmology are too profound to ignore. If correct, it wouldn't just tweak our maps of the universe, it would revolutionize how we understand its origins. Maybe the Big Bang didn't spew matter uniformly, but seeded it in fractal patterns we're only now decoding. Or perhaps gravity's pull over billions of years naturally sculpted chaos into self-similar layers, like wind carving dunes into repeating waves. Either way, fractal cosmology forces us to confront an unsettling possibility. The universe might not be the orderly, predictable expanse we thought. Instead, it could be a vast, cascading tapestry of patterns within patterns, where every zoom inward or outward reveals yet another twist in the cosmic weave. Time crystals sound like something ripped from a sci-fi novel, structures that pulse and oscillate forever without energy, defying one of the most fundamental laws we know, entropy's relentless march toward disorder. Yet this bizarre idea didn't come from fiction. It sprang from the mind of Nobel Prize-winning physicist Frank Wilczek, who dared to ask a revolutionary question. If crystals break the symmetry of space by repeating their atomic patterns, could there be structures that break time's symmetry too? The answer, it turns out, might be yes, and it could rewrite our understanding of reality itself. Imagine a diamond, its atoms locked in an unchanging lattice. Now picture that diamond not just sitting still, but constantly shifting between two states, like a metronome ticking back and forth without any external push. That's the essence of a time crystal, a system that spontaneously oscillates in its lowest energy state, its very structure looping in time like a cosmic clock that never winds down. At first glance, this seems impossible. How can something move without losing energy to friction or heat? The secret lies in quantum mechanics, where particles can exist in superpositions, occupying multiple states at once. In a time crystal, these quantum effects synchronize across countless atoms, creating a dance that persists indefinitely, untouched by entropy's usual decay. Wilczek's idea was initially met with skepticism. Critics argued it violated thermodynamics, but experiments soon proved otherwise. In 2017, teams at Harvard and the University of Maryland created microscopic time crystals using chains of trapped ions or nitrogen vacancies in diamonds. When nudged with lasers, these systems didn't respond at the same frequency as the pulse. They oscillated at fractions of it, a hallmark of time crystalline behavior. It was like pushing a child on a swing and watching them sway at half the speed, a clear break from classical physics. These lab-grown crystals were fleeting, lasting mere fractions of a second, but they confirmed a profound truth. Time symmetry, once thought unbreakable, could be shattered. Now, stretch this concept to cosmic scales. Could the universe harbor natural time crystal structures born from the extreme conditions of neutron stars or the seething vacuum of space? Some theorists speculate that certain quantum fields, stretched by the expansion of the cosmos, might form patterns that repeat not in space but in time, like ripples frozen in the fabric of existence. Others ponder whether dark matter, that elusive invisible stuff binding galaxies together, could exhibit time crystalline properties, its particles cycling through states in a slow, eternal rhythm. The implications are staggering. Time crystals might offer a window into quantum gravity, revealing how spacetime's fabric behaves under extreme conditions. They could even revolutionize technology, serving as ultra-stable components in quantum computers or precision sensors. But perhaps their greatest gift is the way they force us to rethink time itself. We're used to seeing it as an arrow flying inexorably forward. Time crystals whisper that it might also be a loop, a spiral, or a rhythm hidden in the quantum static, a reminder that the universe's secrets often lurk in the spaces between our assumptions. And if tiny crystals in a lab can dance forever, what other marvels might time still hold? Somewhere beyond the stars, hidden behind the thick dust and gas of our own Milky Way, lies a cosmic mystery so powerful it's tugging at thousands of galaxies, including ours, with the gravitational pull of 1,000,000 billion suns. Astronomers call it the Great Attractor, and it's one of the universe's most perplexing enigmas. Imagine throwing a ball into the air only to watch it curve sideways, defying gravity's usual rules. That's essentially what's happening to our galactic neighborhood. Every galaxy within hundreds of millions of light years is drifting toward this invisible behemoth, as if the cosmos itself is tipping toward some unseen drain. What makes the Great Attractor so strange isn't just its power, but its hiding place. It sits in the constellation Norma, buried deep within what astronomers call the zone of avoidance, a region of the sky obscured by the Milky Way's own opaque band of dust, gas, and stars. Peering through this cosmic curtain is like trying to study a distant city through a sandstorm. Early observations could only detect a fraction of the galaxies in this direction, leaving scientists to wonder what monstrous structure could lurk there, pulling everything toward it without revealing itself. Some of the puzzle pieces emerged when astronomers mapped the motions of galaxies using radio waves, which slice through dust where visible light fails. They discovered the Great Attractor isn't alone. It's part of an even larger structure called the Laniakea supercluster, a sprawling web of galaxies spanning 500 million light-years. Within this cosmic metropolis, the Great Attractor acts like a gravitational anchor, with galaxies flowing toward it like rivers into a basin. But here's the twist: Laniakea itself is being pulled toward something even more massive, a distant megastructure whimsically nicknamed the Shapley Attractor. This raises a haunting possibility. The Great Attractor might not be the ultimate force at play, but just one link in a chain of cosmic giants, each tugging the other in a dance we're only beginning to trace. Yet not everyone agrees on what's really happening. Some theorists propose the motion isn't caused by a single structure, but by a vast, uneven distribution of dark matter, a hidden scaffold warping spacetime on scales we've yet to fully map. Others point to dark flow, a controversial phenomenon where clusters of galaxies appear to stream toward the universe's edge at inexplicable speeds, as if something beyond the observable cosmos is pulling them. Could the Great Attractor be a local symptom of this larger mystery, or is it the true epicenter of our galactic drift? New telescopes, like the upcoming Square Kilometre Array, aim to pierce the zone of avoidance with unprecedented clarity, potentially unveiling the attractor's secrets. Until then, it remains a cosmic paradox, a reminder that even as we map the heavens, some forces still loom in the shadows, bending the universe to their will without ever showing their face. And that's the thrill of astronomy. The next great discovery might be hiding in the one place we've barely looked. Imagine a secret tunnel burrowing through the fabric of space itself, a shortcut connecting two distant points in the universe like cosmic subway lines. This isn't just science fiction, it's the tantalizing promise of wormholes, hypothetical bridges through space-time that could, in theory, let you cross the cosmos in a heartbeat. The idea isn't new. Einstein's equations of general relativity hinted at their possibility nearly a century ago, weaving them into the math as Einstein-Rosen bridges. But unlike the monstrous black holes we've come to know, these structures wouldn't just trap matter, they'd transport it, linking star systems or even galaxies in a web of hidden passageways. The catch: wormholes, if they exist, are notoriously unstable. Picture blowing a soap bubble. For a moment, it holds its shape, but the slightest disturbance pops it into nothing. Space-time behaves similarly. A wormhole's throat, the tunnel between its two mouths, would snap shut instantly under the weight of its own gravity, crushing anything trying to pass through. But here's where physics gets wild. To prop the tunnel open, you'd need something called exotic matter, a theoretical substance with negative energy. Unlike ordinary matter, which attracts via gravity, exotic matter would repel, acting like cosmic scaffolding to keep the wormhole from collapsing. Think of it as the universe's version of anti-gravity duct tape, holding the structure together against all odds. Where could such strange material come from? Quantum mechanics offers a clue. The vacuum of space isn't truly empty. It's a seething quantum foam where particles flicker in and out of existence, sometimes borrowing energy from the future in fleeting violations of physical laws. Under the right conditions, these quantum fluctuations might generate the negative energy needed to stabilize a wormhole, at least for a split second. Some theories suggest advanced civilizations could harvest this effect, weaving exotic matter into artificial structures that last longer. Others speculate natural wormholes might already lurk in the universe, forged in the extreme pressures of the Big Bang or threaded through the hearts of black holes hidden from view. But if wormholes are out there, why haven't we found them? The answer lies in their stealth. A stable wormhole wouldn't just look like a glowing portal, it could mimic a black hole's silhouette disguising its true nature. Light bending around its entrance would create telltale distortions, but from a distance, these might blend into the cosmic background. Even stranger, some models suggest wormholes could unzip spacetime in ways that leave faint gravitational wave echoes or peculiar lensing patterns in starlight, hints we might one day detect with sensitive enough instruments. The most mind-bending possibility, wormholes might not just connect places, they could bridge times. A wormhole with one mouth near a neutron star where gravity slows time, and the other in empty space might function as a time machine with seconds passing at different rates on either end. Step through and you could emerge in the past or future, depending on the setup. Of course, this raises paradoxes like the infamous grandfather paradox, where altering the past could erase your own existence. Some physicists argue quantum mechanics would prevent such contradictions, enforcing cosmic censorship to keep causality intact. Others propose wormholes simply can't form in ways that allow backward time travel, no matter how you twist them. Yet for all their paradoxes and puzzles, wormholes captivate because they embody a thrilling truth. The universe's rules might allow for feats we've barely dreamed of. They whisper that the cosmos could be threaded with hidden connections, a labyrinth of shortcuts waiting to be mapped. And while we've yet to find proof they exist, the search itself stretches our imagination, proving that sometimes the boldest ideas, no matter how wild, are the ones that light the way forward. What if the answer to dark matter's riddle isn't some exotic particle, but black holes so ancient they predate the stars themselves? This is the spine-tingling premise of primordial black holes, hypothetical relics from the universe's violent infancy, lurking invisibly in the cosmic shadows. Unlike the stellar mass black holes formed by collapsing stars or the supermassive beasts anchoring galaxies, these would be minuscule, some no heavier than an asteroid yet denser than a mountain. They're thought to have sprung into existence in the first chaotic seconds after the Big Bang, when the infant universe was so hot and dense that random fluctuations could collapse pockets of space directly into black holes. The logic is hauntingly simple. If enough of these primordial traps survived, they could be the invisible mass tugging at galaxies, hiding in plain sight as dark matter. The idea isn't as far-fetched as it sounds. In the 1970s, Stephen Hawking realized that tiny black holes wouldn't last forever. They'd slowly evaporate, leaking radiation in a process now named after him. The smaller the black hole, the faster it vanishes. One with the mass of a mountain would explode in a burst of gamma rays before the first stars even formed. But here's the twist. Black holes heavier than about 1 billion tons could survive to the present day, their decay slowed by their sheer density. If the early universe cooked up enough of these middleweights, they'd be nearly impossible to spot. No light escapes them, and their gravitational footprint would mimic that of diffuse dark matter, perfect cosmic ghosts. The hunt for these phantoms is on. Astronomers have turned to microlensing, a clever trick where a hidden object's gravity bends and brightens light from a background star like a magnifying glass. Teams like the Subaru Telescope's Hyper-Subprime Cam survey have scanned millions of stars, watching for the telltale flicker that might betray a primordial black hole drifting silently through our galaxy. So far, no definitive signal has emerged, but the searchers have tightened the noose, ruling out large ranges of possible masses. Yet the mystery deepens. In 2019, the LIGO gravitational wave detectors picked up something odd. Black holes merging with masses too light to fit standard stellar formation models. Could these be primordial stragglers finally revealing themselves in violent collisions? Debates rage over whether the numbers add up. Some models suggest primordial black holes would have disrupted star clusters or distorted the cosmic microwave background in ways we don't observe. Others counter that they might cluster in halos around galaxies, avoiding these pitfalls. The most thrilling possibility: primordial black holes could come in a spectrum of sizes, from asteroid mass specks to moon-sized monsters, each leaving different fingerprints in the cosmos. There's even a wild fringe idea that one could be hiding in our solar system. Planet 9's gravitational anomalies might not be a planet at all, but a primordial black hole no larger than a tennis ball, its gravity warping the orbits of distant worlds. Whether they're out there or not, primordial black holes force us to rethink dark matter's nature. They remind us that the universe's secrets might not lie in undiscovered particles, but in ancient relics from a time before time, leftover scars from creation itself, woven into the fabric of reality. And if we ever do catch one, it wouldn't just solve a puzzle, it would open a window into the universe's first moments, letting us stare directly into the face of a birth we've only ever imagined. The cosmic microwave background, the afterglow of the Big Bang, should be a random mosaic of hot and cold spots, a fingerprint of the universe's birth with no preferred direction. But in 2005, astronomers studying data from the WMAP satellite stumbled onto something that defied expectations. The fluctuations weren't as chaotic as they should have been. Instead, they seemed to align eerily with the plane of our solar system, as if the universe itself had tipped its hat to Earth. Scientists, with a mix of fascination and unease, dubbed this the axis of evil, a name that captures both its puzzling nature and the threat it poses to cosmology's foundational assumptions. At the heart of the mystery is a concept called isotropy, the idea that the universe looks the same in all directions, no matter where you're standing. It's a cornerstone of modern cosmology, baked into everything from the Big Bang theory to predictions about dark energy. Yet the axis of evil suggests a strange violation of this rule. The alignment isn't just slight, it's as statistically jarring as rolling a die 100 times and getting the same number 90 times. Some researchers argue it's a fluke, a cosmic coincidence amplified by our human tendency to find patterns in noise. Others whisper about more radical possibilities. Could this be a scar from before the Big Bang, or evidence that our universe brushed against another in a long-forgotten collision? The implications spiral out from there. If the axis isn't an illusion, it might hint at a pre-existing structure that survived the Big Bang like a cosmic fossil from a previous cycle of existence. Inflation, the theory that the early universe expanded faster than light, was supposed to erase any such fingerprints, smoothing everything into uniformity. The persistence of this alignment would mean inflation either didn't happen as we thought, or something even stranger overwrote its effects. Then there's the possibility that we're seeing the gravitational tug of a neighboring universe, warping our own like a hand pressing against fabric. Skeptics, though, point to more mundane explanations. Our galaxy's dust, they argue, might subtly distort the CMB in ways we haven't fully accounted for. Or perhaps the anomaly stems from the way we process the data, a glitch in the algorithms rather than the cosmos. Newer observations from the Planck satellite have muddied the waters further. Some alignments seem to persist while others fade, leaving the scientific community split. What makes the axis of evil so compelling isn't just the anomaly itself, but what it represents, a crack in the edifice of our understanding. Science thrives on such cracks, prying them open to reveal deeper truths. Whether this one leads to revolutionary physics or fades into obscurity, it's a reminder that the universe owes us no simplicity. It's free to unsettle, to defy, to whisper riddles we're only beginning to hear. And in those whispers might lie the next great leap or the humbling realization that some mysteries aren't ready to be solved. Every magnet you've ever held, from the one stuck to your fridge to the compass guiding a ship, has two poles, a north and a south. Break it in half and each piece still has both. This symmetry is so fundamental we take it for granted, but what if nature hid a shocking exception? Enter magnetic monopoles, hypothetical particles carrying just one magnetic charge, isolated north or south poles drifting through the cosmos like electrical ghosts. The idea traces back to Paul Dirac in 1931, who realized that quantum mechanics wouldn't just allow for these oddities, it might demand them. His equations revealed a mesmerizing link. If even a single monopole exists somewhere in the universe, it would explain why electric charge comes in fixed, discrete amounts, like cosmic currency with no pennies between. It was as if magnetism and electricity shared a secret handshake, one we'd only glimpse by chasing monopoles, yet decades of searching have turned up empty. Iron-rich minerals in ancient rocks, cosmic rays screaming through the atmosphere, even moon dust brought back by Apollo astronauts, all examined for traces of monopoles, all silent. Their absence isn't just disappointing, it's baffling. Grand unified theories, those ambitious blueprints stitching together all fundamental forces, insist monopoles should have been forged in the universe's first frantic moments. When the cosmos was a seething trillion-degree furnace, the electromagnetic and nuclear forces might have been one and the same. As the universe cooled and these forces froze out, like cracks forming in ice, defects should have arisen, cosmic knots of pure magnetism. Theoretical models suggest we should be knee-deep in these relics, yet every experiment comes up short. So where did they go? One possibility is inflation, that brief period of hyper-expansion right after the Big Bang. If monopoles formed early, inflation might have stretched spacetime so drastically that they were diluted to near non-existence, scattered so thinly across the cosmos that finding one becomes a cosmic needle in a haystack hunt. Another twist, some monopoles could have evolved into strange, extended structures called cosmic strings, their magnetic energy unraveling into filaments that still lace through spacetime today. Or perhaps they're hiding in plain sight, camouflaged within black holes or extra dimensions, their signatures blurred beyond recognition. The hunt hasn't stopped. Experiments like Mo et al. At CERN are pioneering new traps, using superconducting detectors chilled to near absolute zero. When a monopole passes through, it should leave a wake of quantized magnetic flux, a disturbance so distinct it's almost impossible to fake. Other teams scour ancient mica crystals, geological time capsules that could have recorded monopole tracks over millennia like fossilized footprints. Even astrophysicists join the chase, scanning neutron stars for hints that monopoles might have altered their magnetic fields or catalyzed exotic nuclear reactions. What makes monopoles so thrilling isn't just their potential to rewrite physics textbooks. It's the quiet defiance they represent, a reminder that some of nature's simplest questions can upend everything we think we know. Find one and suddenly, forces we assumed were perfectly balanced might tilt, lose the search, and we're forced to ask, did we misunderstand the universe's symmetry, or is the truth still out there, drifting between the stars, waiting to be caught? Either way, the pursuit itself is a testament to science's greatest strength, the courage to chase shadows, knowing one might eventually turn real. What if the Big Bang wasn't a beginning, but a rebound, a cosmic bounce from a previous universe's collapse? This is the breathtaking vision of the Big Bounce, a theory that replaces the singularity of the Big Bang with an endless cycle of expansion and contraction, like a celestial heartbeat pulsing across eternity. At its core lies loop quantum gravity, a radical framework that reimagines spacetime not as smooth and continuous, but as woven from tiny, indivisible threads. These loops, trillions of times smaller than an atom, could provide the scaffolding for a universe that never truly ends, only resets. The allure of the Big Bounce is its elegant solution to one of cosmology's stickiest problems, the singularity. Traditional Big Bang theory hits a wall when we rewind time, compressing all matter and energy into an infinitely dense, infinitely hot point where the laws of physics break down. It's like watching a movie in reverse until the screen glitches into static. No past, no cause, just an unfathomable starting line. But loop quantum gravity offers a way out. In this model, as the universe collapses, the quantum fabric of spacetime resists infinite compression. Instead of a singularity, the universe reaches a maximum density, then bounces like a ball hitting the floor, launching a new phase of expansion. No need for a mysterious beginning, just an eternal rhythm of death and rebirth. Yet the big bounce faces its own hurdles, none more daunting than entropy. The second law of thermodynamics insists that disorder always increases, meaning each cycle should leave the universe more chaotic than the last. How, then, could a reborn universe reset to a smooth, ordered state? Some theorists propose that quantum effects near the bounce could wipe the slate clean, redistributing energy evenly. Others suggest entropy isn't truly erased, but somehow woven into the fabric of each new cycle, leaving subtle imprints across cosmic generations. Imagine a painter starting each canvas with faint traces of the last hidden strokes that only reveal themselves under the right light. The implications ripple outward. If the big bounce is real, our universe might carry echoes of its ancestors. Patterns in the cosmic microwave background, anomalies in the distribution of galaxies, or even the mysterious low entropy of our early cosmos could be relics of a previous iteration. Some models even predict that the laws of physics might tweak slightly with each bounce, meaning our universe's constants. The strength of gravity, the mass of electrons, could be just one roll of the dice in an endless game. But perhaps the most profound shift isn't scientific but philosophical. The Big Bounce trades a single, inexplicable origin for an infinite tapestry of universes, each born from the ashes of the last. It's a vision both humbling and exhilarating, a reminder that endings might be illusions, and that the cosmos, in its grandest scale, could be a story with no first page and no final chapter. Whether the theory holds or falls, it challenges us to rethink not just how the universe began, but whether beginning is even the right word at all. What if our entire universe is nothing more than the interior of a black hole in some higher dimensional cosmos? This mind-bending idea, known as the black hole universe hypothesis, takes the strangeness of black holes and scales it up to reality itself. Picture our cosmos not as an expanding bubble in empty space, but as the warped interior of a colossal singularity, a place where the usual rules of time and space flip inside out. Far from science fiction, this theory emerges from legitimate attempts to reconcile general relativity with quantum mechanics, suggesting that the birth of our universe might have been less like a fireworks explosion and more like a cosmic Russian doll being unpacked from something even grander. The concept builds on holography's radical suggestion that all the information in a three-dimensional space can be encoded on a two-dimensional surface. Apply this to black holes and you get a startling possibility: the event horizon, that point of no return, might not just trap matter but contain a complete description of everything happening inside. Flip this around and the interior of a black hole could manifest as an entire universe, with its own laws of physics emerging from the holographic data stamped on its boundary. In this view, our Big Bang wasn't the beginning of everything. It was the moment a higher dimensional black hole formed, with our universe unfurling within its depths like a flower blooming in reverse. How would this even work? Imagine a four-dimensional star collapsing in a universe with more spatial dimensions than ours. From our limited perspective, the event would appear as a singularity birthing a new spacetime. The expansion we observe could be the stretching of this newborn cosmos as it settles into its strange new geometry. Intriguingly, the equations describing cosmic inflation, the rapid stretching of space after the Big Bang, closely resemble those governing matter falling into a black hole. It's as if the universe's growth mirrors the way space-time distorts near a singularity, but played in slow motion across billions of years. this idea isn't just mathematical poetry. It could explain some of cosmology's deepest puzzles. For instance, why does the universe appear so finely tuned for life? If we're inside a black hole, the conditions might be shaped by the physics of the parent universe, like inheriting traits from a progenitor. Even dark energy, that mysterious force accelerating the cosmos's expansion, could be a relic of the higher dimensional gravity leaking into our reality. Some models suggest the black hole's evaporation via Hawking radiation might eventually influence our universe's fate, linking our distant future to processes we can't yet observe. Critics raise valid concerns, though. If our universe is a black hole's interior, shouldn't we detect signatures of the external cosmos? The answer might lie in scale. Just as a flatlander confined to 2 dimensions can't perceive the third, we might be structurally blind to the higher dimensional arena our black hole calls home. Others question how structures like galaxies could form in such a scenario, but proponents argue the holographic principle allows for complexity to emerge naturally, like intricate patterns forming on the surface of a bubble. The black hole universe hypothesis forces us to confront a humbling thought. We might not just be studying the cosmos, but living inside one of its most enigmatic objects. Whether the theory holds or not, it stretches our imagination to its limits, suggesting that the grandest mysteries of existence might be hiding not in the distant stars, but in the very nature of the space we've always called home. And if true, it would mean every galaxy, every planet, every one of us is part of something far stranger than we ever dared to dream. The Gaia theory shook biology when James Lovelock first proposed it in the 1970s, a daring idea that Earth isn't just a rock hosting life, but a vast, self-regulating system behaving almost like a living organism. Forests regulate oxygen, oceans stabilize temperature, and microbes tweak atmospheric chemistry, all collaborating unconsciously to maintain conditions ideal for life's survival. But what if this isn't just a planetary quirk? What if the entire universe operates the same way, a cosmic-scale Gaia, fine-tuning itself in ways we're only beginning to glimpse? At first glance, the universe seems indifferent, even hostile to life. Yet peel back the layers and eerie patterns emerge. The laws of physics are precariously balanced. Tweak gravity's strength or the neutron's mass by a fraction, and stars couldn't form, atoms would disintegrate, and life as we know it would be impossible. This fine-tuning problem has haunted scientists for decades. Some call it luck, others whisper of design. But theoretical physicist Lee Smolin offers a third option: cosmological natural selection. Imagine black holes as cosmic wombs. When a universe collapses into a singularity, the extreme conditions might trigger a new Big Bang, birthing a daughter universe with slightly tweaked physical constants. Universes that produce more black holes, more offspring, dominate the multiverse over time. In this scenario, our universe isn't fine-tuned for life. It's fine-tuned for black hole production, with life as a curious byproduct. It's Gaia on a grand scale, not a conscious hand guiding things, but a blind, evolutionary mechanism favoring self-replicating structures. Critics pounce on the teleological overtones, the hint of purpose where none may exist. They argue self-regulation implies intent, a slippery slope toward suggesting the universe wants to sustain life. Even Smolin's model has gaps. If universes mutate, why haven't we detected wildly different physics in our cosmic neighborhood? And how does selection pressure operate without some form of replication, a problem biology still grapples with? Yet the theory's brilliance lies in its testability. If black holes are cosmic DNA, their distributions and properties might carry fingerprints of this evolutionary process. Some models even predict universes like ours should have a specific distribution of black hole masses, a pattern astronomers are now scouring the skies to find. The Gaia hypothesis, whether applied to Earth or the cosmos, forces us to confront a radical shift in perspective. It's not just that life adapts to its environment, it's that life and environment co-evolve, locked in a dance that blurs the line between actor and stage. Extend this to the universe, and suddenly, the cold void of space feels less like a passive backdrop and more like an active participant in an epic, self-perpetuating story. Whether the mechanism is Lovelock's biochemical feedback or Smolens's black hole Darwinism, the implication is the same. The universe might not be a sterile arena, but a living, breathing entity, one that spent billions of years learning how to persist. And if that's true, the greatest mystery isn't whether we're alone in the cosmos, but whether the cosmos itself is, in some strange way, alive. Could the universe be nothing more than an ultra-advanced video game running on hardware built by entities we'll never see? This unsettling possibility isn't from a sci-fi novel. It's the simulation hypothesis, a theory that's gained startling traction among philosophers and tech moguls alike. At its core is a simple but profound argument laid out by Nick Bostrom. If any civilization could reach technological maturity without self-destructing, and if they had even slight curiosity about their ancestors, they'd likely create vast simulations of their history. Run enough of these virtual worlds, and the odds tilt overwhelmingly toward us being inside one rather than the original reality. Elon Musk famously quipped the chance we're in base reality is 1 in billions, a cosmic roll of the dice where almost every outcome lands on simulation. But how would we even begin to test such a claim? Some physicists suggest looking for glitches, unexplained limits or anomalies in nature that resemble programming constraints. Take the Planck length, the smallest possible unit of space. Any distance shorter simply doesn't exist in physics. Could this be the universe's pixel size, the resolution limit of whatever's rendering our reality? Then there's the speed of light, nature's ultimate processing speed cap preventing infinite calculations. Even quantum indeterminacy, the way particles blur into probability waves until observed, feels eerily like a video game's lazy loading strategy where details only render when a player looks. The Fermi paradox, the maddening silence where alien civilizations should be, might find grim resolution here. If we're in a simulation, the absence of galactic neighbors could mean our programmers didn't bother populating distant star systems. Or perhaps other civilizations were deleted once they became too resource-intensive, a cosmic control plus Alt plus Del to free up processing power. There's even speculation that attempts to develop artificial superintelligence might trigger built-in safeguards, crashing the simulation to prevent rogue code from escaping its sandbox, a terrifying explanation for why technological leaps often coincide with societal collapses. Yet not all clues point to doom. Some researchers propose actively hacking the simulation. If high-energy particle collisions ever produced unexpected artifacts, say, particles with impossible properties or math that literally doesn't compute, it could betray underlying code. Others hunt for repeating patterns in cosmic constants, like a programmer copy-pasting values across variables. There's even a wild effort to craft messages that would force a buffer overflow, exploiting the system's limits to trigger a detectable error. Whether the simulation hypothesis is genius or madness, it undeniably reshapes how we view existence. It turns physics into reverse engineering, curiosity into a debug tool, and the cosmos into the ultimate black box. And while we may never get definitive proof, the theory's real power lies in the questions it forces us to ask. If this is a simulation, who's running it, and more chillingly, what's their end game? The cosmos is supposed to be expanding evenly, like raisins in rising bread dough, each galaxy drifting apart from the others as space itself stretches. But in 2008, astronomers studying hundreds of galaxy clusters made a spine-chilling discovery. They weren't just drifting, they were flowing, all in the same direction, as if some unseen force beyond the observable universe were tugging them toward the void. This eerie motion, dubbed the dark flow, defies everything we know about cosmic expansion. It's as if the universe has a mysterious tilt, with entire superclusters sliding toward a hidden gravitational anchor we can't see. The evidence comes from the cosmic microwave background, the afterglow of the Big Bang. As galaxy clusters move, their hot gas scatters photons from this ancient light, leaving a faint imprint called the kinematic Sunyaev-Zeldovich effect. By measuring these distortions, researchers led by Alexander Kashlinsky traced the cluster's motion and found they were racing toward a patch of sky near the constellations Centaurus and Vela at speeds exceeding 600 miles per second. The kicker: there's nothing massive enough in that direction to explain the pull. Nothing we can see anyway. This is where things get wild. One explanation is that the dark flow is the gravitational fingerprint of another universe beyond our cosmic horizon. Inflation theory suggests our observable universe is just a tiny bubble in a vast multiverse. If a neighboring bubble brushed against ours long ago, its gravity could have left a permanent distortion, a cosmic wake still tugging at galaxies today. It's like feeling the breeze from a ship you can't see, just beyond the fog. Not everyone's convinced. Skeptics argue the signal might be statistical noise or an artifact of how we map the cosmic microwave background. The Planck satellites later data failed to confirm the original findings at the same confidence level, leaving the mystery unresolved. But Kashlinsky's team insists the flow persists in newer analyses, albeit subtler than first thought. The debate hinges on a deeper question: is this a fluke or evidence that our universe isn't the only game in town? The implications are staggering. If the dark flow is real, it's not just a curiosity, it's a crack in the doorway to the multiverse. We might be witnessing the first hints of a reality beyond our cosmic walls, where other universes loom like shadowy giants, their gravity reaching across dimensions to stir the fabric of our own. Whether the data holds up or not, the dark flow reminds us that the universe's greatest secrets might not lie in the stars, but in the unseen currents tugging them toward the unknown. Time might be the most persistent illusion of all. Physicist Julian Barber's radical theory strips it away entirely, proposing that the universe isn't a movie playing frame by frame, but a frozen gallery of moments, each a complete, self-contained now, stacked like snapshots in a cosmic album. In this timeless vision, change isn't fundamental. It's a trick of perspective, like mistaking a flipbook's animation for real movement when all that exists are static pages. Barber calls these slices nows, and in his framework, the entire history of the cosmos is just a vast collection of them, with no past or future, only an infinite mosaic of frozen instances. This idea didn't spring from metaphysics but from the gritty math of quantum gravity. When physicists try merging general relativity with quantum mechanics, time often vanishes from the equations entirely, leaving behind a block of unchanging relationships. Barber seized on this, arguing that what we experience as time isn't a flowing river but a series of quantum correlations between these nows. Causality, the chain of cause and effect we rely on to make sense of reality, wouldn't be a fundamental law but an emergent property, like temperature arising from the chaotic dance of atoms. Think of it like reading a novel. The story only makes sense because your brain links the words in order, but the book itself just sits there, its pages eternally fixed. The implications are dizzying. If time isn't real, then the Big Bang isn't an event in the past, it's just one now among others, forever locked in relation to the rest. Your childhood, your future, even the heat-death of the universe would all exist simultaneously, like landmarks on a map you're navigating without moving. This challenges not just physics but philosophy. How does free will operate if the future is already out there? Barber suggests it's a matter of perspective. Just as a hiker can choose which mountain peaks to focus on while the landscape itself never changes, our consciousness might move through nows, creating the illusion of time's passage. Critics argue this smacks of solipsism, a universe where nothing ever happens. But Barber's model offers elegant solutions to thorny problems. Take quantum superposition, where particles exist in multiple states until measured. In timeless physics, the measurement isn't a moment in time but a correlation between nows, sidestepping the need for wave function collapse. Even entropy, the arrow of time's secret engine, could arise from the statistical arrangement of nows, like finding order in a shuffled deck of cards. The real test, finding timeless signatures in quantum gravity experiments. Some proposals suggest that if space-time is pixelated at the Planck scale, as loop quantum gravity predicts, those fundamental grains might not carry timestamps at all, just relational data. Future detectors hunting for quantum foam or anomalies in black hole radiation could stumble on clues. Until then, Barber's vision remains a haunting provocation that our most visceral experience, the relentless march of seconds, might be the universe's most convincing mirage, a story we tell ourselves to make sense of a reality that simply is. And if true, it means the end of time isn't a catastrophe, it's the revelation that time never began in the first place. What if the chaos we see in the universe is just the surface of something far more structured, a hidden layer of reality where everything is seamlessly connected? This is the heart of physicist David Bohm's implicate order, a radical reimagining of existence that turns our everyday experience on its head. Picture a hologram where every tiny fragment contains the whole image. Now stretch that idea to the cosmos. Bohm proposed that what we perceive as separate objects, planets, people, particles, are just temporary unfoldings from a deeper, enfolded dimension, like ripples emerging from an infinite ocean. In this view, the universe isn't a collection of isolated things, but a dynamic dance of wholeness, constantly folding and unfolding into the reality we recognize. The inspiration came from quantum entanglement, that eerie phenomenon where particles instantaneously influence each other across vast distances, defying classical notions of space and time. Einstein famously called it spooky action at a distance, but Bohm saw it as a clue. If particles behave as if they're part of a unified whole, perhaps separateness is the illusion. His implicate order suggests that at the fundamental level, everything is interconnected, with the apparent boundaries between objects merely projections of a deeper, invisible fabric. Think of it like watching a whirlpool in a river. It appears distinct, but it's really just a pattern in the water, inseparable from the flow itself. Critics, however, bristle at the non-locality implied by Bohm's model. Mainstream physics prefers frameworks where causality respects the speed of light, avoiding what some dismiss as mystical overtones. Yet Bohm's ideas persist, fueled by experiments that keep confirming entanglement's defiance of classical logic. Some researchers even speculate that the implicate order could explain consciousness itself, that our sense of self might arise from this deeper layer, like a wave cresting momentarily from the sea before dissolving back into it. Bohm's vision doesn't just challenge physics, it reshapes how we see existence. If the implicate order is real, then chaos and fragmentation are surface phenomena, illusions born from our limited perspective. Beneath it all, the universe might be a cosmic symphony, each note, every atom, every star, an expression of a hidden harmony we're only beginning to hear. And that changes everything from how we study quantum particles to how we understand our place in the vast, shimmering whole. What if the universe isn't just governed by physics, but is itself a kind of cosmic brain? This startling idea, gaining traction among a small but bold group of physicists, suggests that space-time and quantum mechanics might emerge from something even more fundamental, a vast universe-spanning neural network. Picture the intricate connections in your own brain, where billions of neurons fire in complex patterns to create thoughts and sensations. Now imagine scaling that up to cosmic proportions, with every particle, every force, every flicker of reality arising from the interactions of nodes in an incomprehensibly large web of information. It's a theory so radical it blurs the line between physics and computer science, proposing that the cosmos might not just resemble a neural network, it could be one. The idea gained serious momentum in 2018 when physicist Vitaly Vanchorin published a paper suggesting that deep learning systems, the same algorithms powering today's AI, might inadvertently mimic the behavior of quantum mechanics when scaled to extreme complexity. His work hinted at a wild possibility. The same mathematical structures governing neural networks could underpin the universe's deepest laws. Later models expanded this further, showing how spacetime itself might emerge from these connections, like a three-dimensional projection of higher-dimensional data. In this view, particles aren't tiny billiard balls but nodes in the network, their interactions governed by weights and activations rather than traditional forces. Even gravity could be a byproduct, not a fundamental force, but a statistical tendency of the network to optimize its structure over time. Critics, of course, push back hard. Traditionalists argue this smacks of metaphor over mechanism, swapping one mystery for another without concrete predictions. How do you test whether reality is computational? Detractors also point to Occam's razor. Why invoke an abstract neural network when existing frameworks like quantum field theory already describe the cosmos with precision? But proponents counter that neural networks might solve lingering puzzles. Take quantum entanglement, where particles instantaneously influence each other across vast distances. In a neural cosmos, this spooky action could simply be nodes sharing hidden layers of connection, no stranger than two thoughts firing in tandem across your brain's synapses. The debate taps into a deeper tension in physics. Is the universe fundamentally mathematical or informational? For decades, we've treated physical laws as equations etched into the fabric of reality. The neural network theory flips this, suggesting those laws are more like emergent software, running on hardware we've yet to comprehend. Some researchers even speculate that if the cosmos is a network, its training data might be detectable subtle glitches in quantum behavior or unexpected symmetries in particle collisions that hint at an underlying architecture. Whether the neural universe holds water or not, its boldness is undeniable. It reframes existence not as a stage for particles and forces, but as a dynamic, self-organizing system, one that might think, learn, or even evolve in ways we're only beginning to imagine. And that raises a tantalizing question. If the universe is a network, who or what is the programmer? The answer might not lie in some external designer, but in the network's own capacity to rewrite its rules, forging reality not from the top down, but from the connections outward. The universe isn't just expanding, it's accelerating, as if some invisible force is pressing harder on the cosmic gas pedal with every passing moment. That force, dark energy, has long been a mystery, but what if its true nature is even stranger than we guessed? Enter the phantom universe, a theory so unsettling it suggests dark energy isn't just pushing galaxies apart but growing stronger over time, destined to tear space-time itself apart at the seams. The key lies in a deceptively simple number, W, the equation of state for dark energy. In most models, W equals -1, meaning dark energy's density stays constant as the universe expands. But if W dips below that threshold into what physicists call phantom energy, the rules of the game change dramatically. Instead of merely accelerating expansion, phantom energy would amplify itself, becoming denser as space stretches, like a fire that grows hotter the more it spreads. The end game of this runaway process is the Big Rip, a cosmic doomsday scenario where phantom energy's grip tightens until it overpowers every force holding reality together. First, galaxy clusters would be yanked apart, their gravitational bonds no match for the escalating push. Then, individual galaxies would unravel, stars flung into the void like sparks from a bonfire. As the phantom tide rises, solar systems would disintegrate, planets torn from their orbits. In the final moments, even atoms wouldn't be spared. the bonds between protons and electrons would snap, nuclei would shatter, and space-time itself would fracture into a sea of disconnected particles, each isolated in a suddenly infinite void. It's not just the death of matter, but the dissolution of the stage upon which reality plays out. What makes this theory so chilling isn't just its inevitability, it's the eerie hints that it might already be happening. Some measurements of distant supernova, the cosmic lighthouses used to track the universe's expansion, show anomalies consistent with W values below -1. These observations are still debated. Instrumental errors or statistical flukes could explain the data, but if confirmed, they'd imply phantom energy isn't hypothetical. It's here, lurking in the shadows of our equations, silently tightening its grip. Critics argue that phantom energy violates fundamental energy conditions, creating paradoxes where causality breaks down. Yet in quantum field theory, negative energy densities aren't just possible, they've been observed in lab experiments like the Casimir effect, where the vacuum between two plates teems with phantom-like fluctuations. Could the universe be scaling up this phenomenon, turning a quantum quirk into a cosmic death sentence? The phantom universe forces us to confront a haunting question. Is the cosmos not just expanding but unraveling? Whether the data ultimately supports this scenario or not, it reminds us that dark energy isn't just a passive backdrop, it's the wild card that could rewrite the universe's final chapter. And if the Big Rip is real, the clock is already ticking, not toward collapse or cold stagnation, but toward a finale where space-time itself is the casualty. What if, at the very instant our universe was born, an exact mirror version erupted into existence alongside it? A perfect reflection where time flows backward, matter is antimatter, and left becomes right. This isn't science fiction, it's the startling prediction of CPT symmetry, one of the most ironclad principles in physics. The idea hinges on a cosmic balancing act. For every particle spinning clockwise in our world, there should be an identical twin spinning counter-clockwise in the mirror universe. Yet if this twin exists, where is it? And how could an entire cosmos of antimatter stars and planets remain utterly hidden from view? The answer might lie in the universe's earliest moments, when a split-second cosmic tug of war sent the two realities racing apart, never to meet again. CPT symmetry, short for charge parity and time reversal, is the ultimate cosmic fairness rule. It states that if you flip a particle's charge turning matter to antimatter, mirror its spatial coordinates, left becomes right, and reverse the flow of time, the laws of physics should stay identical. This isn't just theory. Experiments with subatomic particles confirm it holds with near-perfect precision. But here's the twist. While our universe is overwhelmingly made of matter, CPT demands a counterweight. If the Big Bang truly created equal parts matter and antimatter, as physics insists, then the antimatter didn't just vanish. It might have been shunted into its own parallel cosmos, forever separated by the hyper-stretching of cosmic inflation. Imagine two soap bubbles blowing apart in opposite directions, each carrying a universe inside, one made of the stuff we know, the other its perfect inversion. The mirror universe could solve one of physics' most persistent headaches, the neutrinos' baffling behavior. These ghostly particles oscillate between three flavors as they travel, but experiments show they do this more dramatically than the standard model predicts. If neutrinos are secretly interacting with their mirror counterparts, particles we can't see but whose influence leaks through, it would neatly explain the anomaly. Some models even propose that sterile neutrinos, hypothetical particles that refuse to interact with normal matter entirely, could be the bridge between the two universes, flickering briefly into ours like shadows cast from another dimension. Yet if the mirror universe is out there, why can't we see it? Inflation offers a clue. In the first fraction of a second after the Big Bang, space itself expanded faster than light, stretching regions of the primordial fireball so far apart that no signal could ever cross the gap. Our antimatter twin may lie beyond an impassable horizon, its light forever too distant to reach us. Even gravity, which penetrates all known barriers, might not escape this divide. Some theories suggest inflation could have severed spacetime itself, leaving the two universes causally disconnected, like islands in separate oceans. The implications are staggering. If the mirror cosmos exists, it wouldn't just be a curiosity, it could rewrite our understanding of the Big Bang's aftermath. Perhaps matter didn't win over antimatter in our universe due to some exotic particle asymmetry. Maybe both survived equally, just in separate realms. Some researchers speculate that black holes could be portals between the two, their singularities folding spacetime into knots where matter and antimatter briefly touch. Others wonder if dark matter's elusive nature stems from particles that straddle both realities, tugging on our universe from the shadows of its reflection. The mirror universe remains a tantalizing what-if, but it's one with growing traction. Experiments like the Deep Underground Neutrino experiment are hunting for anomalies that could hint at sterile neutrinos, and by extension, their mirrored cousins. Meanwhile, astrophysicists scour the cosmic microwave background for odd patterns that might betray an unseen gravitational tug from the other side. Whether the theory holds or not, it forces us to confront a humbling possibility. The cosmos might not just be stranger than we imagine, but stranger than we can imagine, with every particle, every force, every law of physics we hold dear echoed perfectly, yet irreachably somewhere beyond the edge of everything we know. Imagine the universe not as an endless expanse, but as a colossal donut, a three-dimensional torus where if you traveled far enough in one direction, you'd eventually loop back to where you started. This isn't a cosmic fantasy, it's a serious proposal in the study of topology, the branch of mathematics that explores shapes and their properties. A toroidal universe would be finite yet unbounded, meaning it has a limited volume but no edges, no boundaries. You could sail through space forever without hitting a wall, yet the cosmos wouldn't be infinite. It's the same principle as a video game world that wraps around, fly far enough to the right, and you reappear on the left. But if space is shaped like a torus, why doesn't the night sky show obvious repeats, like duplicate galaxies or echoes of the Big Bang? The answer lies in scale and the limitations of our perception. The cosmic microwave background, that faint glow from the dawn of time, could hold subtle clues. In a toroidal universe, light would have multiple paths to travel, wrapping around the donut's curves. This could create faint, repeating patterns in the CMB like Hall of Mirrors reflections buried in the static. Researchers have hunted for these ghostly duplicates, scanning the sky for matching circles of temperature fluctuations that would betray the universe's true shape. Some tantalizing hints emerged in early data from the WMAP and Planck satellites, but the evidence remains controversial. The patterns could just as easily be statistical flukes, cosmic noise masquerading as structure. The real challenge is that if the universe is a torus, it's likely so vast that the repeating patterns are stretched beyond our observational horizon, like a fingerprint smeared across light years. There's another twist. The universe's expansion could be masking its topology. Even if space is fundamentally donut-shaped, the relentless stretching of spacetime since the Big Bang might have inflated any recognizable repeats to scales too large to detect. Imagine blowing up a balloon with a tiny pattern, stretch it enough, and the design becomes imperceptible. This cosmic hide-and-seek leaves scientists grappling with a haunting question. If the universe is finite, how could we ever prove it? One promising avenue is gravitational waves. These ripples in spacetime, generated by colliding black holes, might carry imprints of the universe's global shape as they propagate, their waveforms subtly distorted by looping around a toroidal geometry. Future observatories, like the proposed LISA mission, could have the sensitivity to catch these whispers of curvature. The torus isn't the only possible shape either. Topologists have imagined the universe as a hyperdimensional pretzel, a twisted Klein bottle, or even a sprawling honeycomb of interconnected chambers. Each configuration would leave distinct fingerprints in the fabric of reality. A Klein bottle universe, for instance, would lack an inside or outside, just a single continuous surface where space folds in on itself like a Möbius strip scaled to cosmic proportions. These shapes aren't just mathematical curiosities, they're testable hypotheses. If the universe is finite, its geometry would influence how light, gravity, and even quantum fields behave on the largest scales. Yet the implications go beyond mere geometry. A finite universe would mean everything we see, every galaxy, every quasar, is just one copy in a potentially repeating cosmic tapestry. It would redefine our place in the cosmos, not as a speck in an infinite void, but as a thread woven into a vast but closed loop. Whether space is a torus, a sphere, or some more exotic form, the quest to map its true shape is really a search for the universe's deepest architecture, the hidden blueprint underlying everything we perceive. And until we find definitive proof, the question lingers: is our universe an endless expanse, or are we all, in some strange way, traveling in circles? At the heart of our cosmic confidence lies an unsettling question: what if everything you remember, every star you've seen, every law of physics you trust, is just a fleeting hallucination of a single, disembodied mind? This is the chilling paradox of the Boltzmann brain, a thought experiment so unnerving it threatens to unravel not just cosmology, but the very foundation of reality as we know it. The premise hinges on a simple statistical quirk. In an infinite universe governed by entropy, random thermal fluctuations can momentarily assemble complexity from chaos. Given enough time, even the most improbable events become inevitable, including the spontaneous formation of a fully conscious brain, complete with fabricated memories of a life that never existed. And here's the kicker: mathematically, it's infinitely more likely for a lone brain to pop into existence than an entire ordered universe like ours. The nightmare begins with Ludwig Boltzmann, the 19th century physicist who first grappled with entropy's arrow. He realized that while disorder tends to increase, tiny pockets of order can emerge by chance, like eddies in a rushing river. Fast forward to modern cosmology, and this principle takes a surreal turn. In an eternally expanding universe, quantum fields never truly settle. They jitter endlessly, occasionally arranging particles into coherent structures purely by accident. A single self-aware mind floating in the void requires far fewer particles to align than galaxies, planets, and 11 billion years of cosmic history. Statistically, you're far more likely to be that lone fluctuation, a momentary spark of consciousness mistaken for a person in a world that doesn't exist than a being in a real universe. This isn't just philosophical musing. The Boltzmann brain poses a direct challenge to how we test cosmological theories. If a model predicts an old, vast universe where Boltzmann brains outnumber ordinary observers, does that invalidate the model? Some physicists argue yes, wielding the paradox as a razor to slice away hypotheses that lead to absurd observer statistics. Inflationary cosmology, for instance, had to be tweaked to avoid spawning endless Boltzmann brains in its eternal multiverse. Even quantum mechanics gets dragged into the fray. If consciousness plays a role in collapsing wave functions, as some interpretations suggest, could a Boltzmann brain's illusory observations create its own reality? Yet the paradox has loopholes. One escape route is the anthropic principle. Perhaps universes where brains spontaneously form are inherently unstable, collapsing before they can falsely remember coherent physics. Another hinges on quantum decoherence. Random fluctuations might assemble a brain, but maintaining its structured thoughts long enough to ponder its existence could be exponentially harder. There's also the grim timeline. In a universe destined for heat death, Boltzmann brains would overwhelmingly emerge in the distant, cold future when entropy reigns. The fact we observe a relatively young, energy-rich cosmos might hint we're not late-arriving flukes after all. The real sting of the Boltzmann brain isn't just its threat to science, it's how it hijacks our trust in perception. Every memory, every scientific measurement could be noise masquerading as signal. But here's the twist: the paradox might actually validate the scientific method. If we're all hallucinations, why does physics hold together so perfectly? Why do our collective, false memories align? The very consistency we fear is fake could be the best evidence it's real. In the end, the Boltzmann brain isn't just a crisis, it's a mirror, forcing us to confront why we believe anything exists at all. And that's a mystery no random fluctuation can easily explain. Black holes have long been the universe's ultimate cosmic sinks, regions where matter and light vanish forever, crushed into oblivion by gravity's unforgiving grip. But what if their opposites exist too? Enter the white hole, a hypothetical cosmic geyser where matter and energy erupt outward instead of collapsing inward, a place where nothing can enter, only escape. Now imagine this: our entire universe might be the aftermath of a white hole's violent birth. This radical theory flips the Big Bang on its head, proposing that the explosive beginning of everything wasn't a singularity's collapse but a white hole's explosive release, a cosmic reset button forged in the fires of quantum gravity. The math behind white holes isn't science fiction. They emerge naturally from Einstein's equations of general relativity as the time-reversed twins of black holes. Where a black hole's event horizon is a one-way street leading to doom, a white hole's horizon is an exit door with no entrance, a fountain of space-time spewing matter and light into existence. For decades, physicists dismissed them as mathematical curiosities, since nothing in nature seemed to explain how they could form. But loop quantum gravity, a leading theory aiming to unify quantum mechanics and general relativity, breathes new life into the idea. In this framework, a black hole's crushing singularity might rebound into a white hole when quantum effects take over, like a compressed spring finally snapping back. The result, a Big Bang-like eruption, birthing a new cosmos from the ashes of a collapsed one. The implications are staggering. If our universe sprang from a white hole, it could explain the inexplicable uniformity of the cosmic microwave background. The violent, high-energy ejection would have scrambled any pre-existing structure, leaving behind the smooth, hot soup of particles we observe in the early universe. Even dark matter finds a potential origin here. Some models suggest white holes could eject exotic particles not found in our standard cosmic recipe, remnants of whatever strange physics govern the parent universe. Yet white holes come with cosmic paradoxes. If they're truly one-way exits, how could anything trigger their formation? One possibility lies in the quantum tunneling, a process where particles leap through seemingly impossible barriers. A black hole trapped in its own gravitational prison might quantum tunnel into a white hole over astronomical timescales, trading collapse for eruption. Observations might even bear this out. Some astrophysicists speculate that fast radio bursts, those mysterious millisecond blasts of radio waves from deep space, could be white holes flickering to life, ejecting energy before snapping shut again. The most tantalizing clue, though, might lie in the cosmic microwave background itself. If our universe is a white hole's aftermath, its earliest moments could carry subtle imprints of the parent black hole's demise, anisotropies or polarization patterns distinct from standard inflation predictions. Future telescopes hunting for primordial gravitational waves could stumble upon these fingerprints, revealing a cosmos not just born but reborn. Whether the white hole universe theory holds or not, it challenges our deepest assumptions about beginnings and endings. It suggests that creation might not be a singular event but a cosmic cycle, where every end contains the seed of a new reality. And if true, it means we're not just stardust, we're the echoes of a singularity's final cry, the aftermath of a physics so extreme it birthed existence itself. The universe is supposed to be the same in every direction, no preferred axis, no cosmic North Star, just an even distribution of matter obeying the principle of isotropy. Yet when astronomers began mapping the spins of millions of spiral galaxies, they stumbled onto something unsettling. A fraction of these galaxies appeared to align their rotation axes as if guided by an invisible cosmic current. This observation sparked a radical question. Could the universe itself be rotating, dragging galaxies along in a slow, silent whirl? At first glance, the idea seems absurd. The standard cosmological model treats the universe as isotropic, meaning its large-scale structure looks identical no matter where or which way you look. A rotating universe would violate this symmetry, introducing a preferred direction like a vast, invisible vortex twisting spacetime itself. Early hints of this anomaly came from studies like the Sloan Digital Sky Survey, where researchers noticed that certain galaxy spins weren't randomly oriented as expected. Instead, they showed slight but statistically significant alignments across billions of light years, as if some vast, unseen torque were nudging them into coherence. Critics were quick to pounce. Galaxy formation is messy, shaped by local gravitational tugs and collisions that could easily create the illusion of large-scale order. Others pointed to observational biases. Maybe telescopes were inadvertently favoring aligned galaxies in certain sky regions. But the most damning evidence against a rotating universe comes from the cosmic microwave background, the afterglow of the Big Bang. If the cosmos were spinning, the CMB's temperature fluctuations would show distinct dipole patterns, like smeared brushstrokes along the axis of rotation. Instead, the CMB remains stunningly uniform, its anisotropies random and isotropic to within 1 part in 100,000. So why do some galaxies still seem to twirl in sync? One compelling explanation involves cosmic filaments, the immense threads of dark matter weaving the universe's large-scale structure. As galaxies form along these filaments, their angular momentum can be influenced by the filament's gravitational shear, subtly aligning their spins like leaves caught in a river's flow. Supercomputer simulations support this, showing that even in an isotropic universe, the tidal forces from these colossal structures can imprint faint correlations in galaxy rotation. Another possibility is that we're seeing the ghostly imprint of primordial magnetic fields, relics from the universe's infancy that could have gently coaxed spinning gas clouds into alignment during the cosmos's formative years. Yet the allure of a rotating universe persists, if only as a thought experiment. General relativity doesn't forbid it. Solutions like the Gödel metric describe rotating universes where time loops back on itself, though these models require exotic physics like closed time-like curves. Some theorists even speculate that a universe born from a black hole might inherit spin from its progenitor, carrying a faint rotational whisper into its expansion. But until evidence emerges that can't be explained by filaments, magnetism, or noise, the verdict leans heavily toward a still, stately cosmos, one where any rotation is local, not cosmic. The deeper lesson here isn't just about spin, it's about how science grapples with anomalies. Every outlier, every oddity, is a chance to test the boundaries of our understanding. Sometimes, like with galaxy alignments, the anomaly fades under scrutiny, absorbed into the existing framework. Other times, it cracks that framework wide open. And in that tension between the expected and the inexplicable lies the thrill of discovery, the reminder that the universe always has another secret waiting just beyond the edge of our maps. Black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate shredders, swallowing stars, planets, and light with no apparent way to retrieve what's lost. But here's the problem. Quantum mechanics insists information can never be truly destroyed, while general relativity claims black holes erase it completely. This contradiction, known as the information paradox, haunted Stephen Hawking for decades until his final papers proposed a revolutionary solution. Imagine a black hole's event horizon not as a smooth, featureless boundary, but as a seething wall of quantum chaos, a firewall of ultra-energetic particles scrambling data into holographic code. It's as if the universe, faced with an impossible choice between two fundamental laws, forged a third path, one where information isn't lost, but rewritten into a language we're only beginning to decode. Hawking's breakthrough built on the holographic principle, the radical idea that all the information falling into a black hole gets imprinted on its surface, like a cosmic DVD encoding three-dimensional reality onto a two-dimensional plane. This isn't just metaphor, it's grounded in the AD-S/CFT duality, a mathematical framework showing how a black hole's interior, the bulk, can be perfectly described by quantum fields living on its boundary. Picture a theater where the actors on stage are mere projections of a script written backstage. In this analogy, the script is the boundary theory CFT, and the actors are the events unfolding inside the black hole AD-S. The duality suggests information never actually enters the black hole. It's just translated, preserved on the horizon in a form so scrambled it looks like noise. But how does this solve the paradox? Enter Hawking radiation. As black holes emit particles, they slowly evaporate, seemingly erasing the information they consumed. Hawking once thought this radiation was random, pure thermal noise with no hidden structure. But if the holographic principle holds, that radiation isn't random at all. It's carrying the very information once thought lost, meticulously encoded in subtle quantum correlations between emitted particles. Think of it like burning a book. To a bystander, the ashes seem meaningless, but with perfect knowledge of the fire's physics, you could reconstruct every word. Similarly, Hawking's final work suggested black holes might leak information through their radiation, not by preserving the original data, but by weaving it into the fabric of spacetime itself. The most contentious piece of this puzzle is the firewall hypothesis. If information stays on the horizon, what happens to an astronaut falling in? Quantum mechanics demands they see empty space, while the holographic principle implies they'd hit a blazing curtain of high-energy particles, a firewall born from the clash of competing physics. Some theorists argue this paradox reveals a flaw in our understanding of locality, the idea that objects are only influenced by their immediate surroundings. Others propose gentler resolutions like quantum entanglement, smoothing the firewall into a fuzzball, a tangled string theory, inspired structure where the black hole's interior dissolves into a knot of vibrating strings, preserving information without violent drama. The implications ripple far beyond black holes. If information is truly holographic, spacetime itself might emerge from quantum bits living on some distant surface, like a 3D projection of a 2D code. This reshapes how we view everything from the Big Bang to dark energy, suggesting the universe's deepest laws might not be about forces or particles, but about information flow. Even Hawking's final paper, co-authored with Andrew Strominger, hinted at cosmic, soft-hair, low-energy quantum imprints on black hole horizons that could store data in subtle, previously unnoticed ways. Yet mysteries remain. If information escapes black holes, where's the experimental proof? Future gravitational wave detectors might catch hints in the ring-down of merging black holes, subtle vibrational tones encoding their holographic secrets. Or perhaps quantum computers could simulate AD-S/CFT duality, testing whether boundary theories really predict bulk physics. Either way, the paradox's resolution, whether firewalls, fuzzballs, or something stranger, doesn't just save information. It redefines reality, suggesting the universe is less a collection of objects than a dynamic network of data, where even the darkest voids are whispering their stories, if only we learn to listen. Imagine the universe as a cosmic ledger, where every bit of matter and energy is balanced by an equal and opposite entry, a grand equation where the sum total of existence might add up to absolutely nothing. This is the startling premise of the zero-energy universe, a theory suggesting that all the stars, galaxies, and even dark matter are offset by the negative pull of gravity, leaving the cosmos with a net energy of zero. It sounds like accounting magic, but the idea emerges straight from Einstein's equations, where gravity isn't just a force, it's the curvature of spacetime itself, carrying its own energy budget. Picture a balloon inflating. The positive energy of the stretched rubber is perfectly cancelled by the negative pressure inside, leaving the system energetically neutral. Now scale that up to the universe, and you've got a reality where everything we see could be the universe's way of balancing its own books. The math hinges on a profound symmetry. Every particle of matter carries positive energy, thanks to Einstein's E equals mc squared, but gravity, with its relentless pull, acts like a cosmic debt negative energy that counters the ledger. The more mass you add to the universe, the stronger this gravitational negative grows, keeping the total sum locked at zero. Even the expansion of space plays a role. As the universe stretches, the energy tied up in matter gets diluted, but the negative gravitational energy scales precisely to match. It's as if the cosmos is a self-correcting equation, perpetually resetting to equilibrium. Where does this zero-sum game begin? The answer might lie in the quantum vacuum, that seething, invisible ocean of energy underlying all of space. According to quantum field theory, empty space isn't truly empty, it's a chaotic dance of virtual particles popping in and out of existence, borrowing energy from the future in fleeting violations of conservation laws. These quantum fluctuations could have birthed the entire universe in a process called vacuum genesis, where a tiny bubble of space-time tunneled into existence from nothingness, fueled by the vacuum's borrowed energy. Once the bubble inflated, its positive matter energy and negative gravitational energy cancelled out, leaving the universe with zero net cost, a cosmic free lunch, as physicist Alan Guth famously quipped. Critics argue that calling the universe zero energy is a clever accounting trick, since we can't actually measure the total energy of an infinite, expanding cosmos. But supporters counter that the principle holds even on observable scales. Take a collapsing star. As it implodes into a black hole, its positive mass energy is counterbalanced by the hole's negative gravitational binding energy, leaving the system's total energy unchanged. This symmetry isn't just theoretical, it's baked into the fabric of general relativity, where the curvature of space-time and the distribution of mass and energy are two sides of the same coin. The zero-energy hypothesis doesn't just rewrite our origin story, it reshapes how we think about the universe's fate. If the cosmos truly sprang from nothing, then its ultimate fate, whether a big freeze, a big crunch, or a big rip, might just be the ledger settling back into perfect balance. Some models even suggest that new universes could continually bubble up from the quantum foam, each a self-contained zero-energy fluctuation in an endless sea of nothingness. It's a humbling thought. Everything we know, the swirl of galaxies, the glow of starlight, even the spark of consciousness, might just be an intricate dance between positive and negative, a fleeting symmetry in the void's infinite ledger. And if that's true, then the greatest mystery isn't why there's something rather than nothing, it's why that something feels so real. What if consciousness isn't something the brain creates, but a fundamental feature of reality itself, like space, time, or gravity? This is the radical proposition of panpsychism, a theory that flips our understanding of the mind upside down. Instead of treating consciousness as an accidental byproduct of complex computation, a glitch in the neural machinery that evolution stumbled upon, panpsychism suggests it's woven into the fabric of the universe at the most basic level. Particles, atoms, even stars might possess some dim, primordial form of awareness, with human thought merely representing a highly organized version of this universal substrate. It's an idea that sounds more at home in philosophy than physics, yet it's gaining traction as scientists grapple with the so-called hard problem of consciousness. Why does subjective experience exist at all? The appeal lies in its elegance. Physics describes the universe with stunning precision, from quantum fluctuations to galactic superclusters, yet it's utterly silent on why any of this should feel like something from the inside. A brain processes information, but why should that processing come with the taste of coffee, the sting of loss, or the awe of a starry sky? Panpsychism sidesteps this puzzle by removing the need for consciousness to emerge from non-conscious parts. If experience is fundamental, then the problem isn't how matter gives rise to mind. It's how simple, scattered flashes of awareness combine into the rich, unified streams we recognize as our own. Imagine trillions of tiny sparks coalescing into a flame. That's panpsychism's vision of the mind, a symphony of micro-experiences harmonizing into self-reflection. But how do you test such a theory? Critics argue it's untestable by definition. If consciousness is everywhere, how could we ever isolate or measure it? Supporters counter that panpsychism makes subtle predictions about the nature of quantum systems, where observation seems to play an inexplicable role in shaping reality. Some interpretations of quantum mechanics, like von Neumann-Wigner's, even suggest consciousness collapses the wave function, implying a deep link between mind and matter. Others point to integrated information theory, which quantifies consciousness as a property of systems with high phi, a measure of how interconnected and irreducible their information processing is. Under this framework, even simple devices like thermostats might possess infinitesimal phi, hinting at a spectrum of awareness stretching from atoms to humans. The most controversial implication: if consciousness is universal, then the cosmos itself might be aware in some diffuse, inscrutable way, not as a single, godlike mind, but as a vast network of micro-experiences, a universe that doesn't just contain consciousness but is consciousness. This isn't mysticism, it's a challenge to materialism's assumption that matter is all there is. Philosopher Galen Strawson sums it up bluntly: real physicalism, the belief in a purely physical universe, requires panpsychism, because denying consciousness's fundamentality means accepting magic. That experience somehow pops into existence from nowhere. Yet the theory's beauty is also its weakness. Without a clear bridge between microscopic awareness and macroscopic minds, panpsychism risks explaining nothing by claiming everything is conscious. And if electrons have inner lives, what does that even mean? Defenders argue we're trapped by language. Our vocabulary for experience is built for human minds, not quantum fields. But until we find empirical hooks like quantum signatures of observation or anomalies in information processing, panpsychism remains more metaphysics than physics. Still, its allure persists because it dares to ask the question science often avoids. What if the universe isn't just a clockwork mechanism, but a living tapestry of experience? Whether panpsychism holds or not, it forces us to confront the eerie possibility that the cosmos might not just be observed, it might be observing, and that changes everything. From cosmic strings threading the void like cracks in space-time to the holographic principle suggesting our 3D reality might be a cosmic projection, we've journeyed through theories that don't just stretch the imagination, they shatter it. Each one challenges the bedrock of what we think we know, turning the universe from a predictable stage into a labyrinth of hidden doors. Consider the black hole universe hypothesis, where our entire cosmos could be the interior of a singularity, or the zero-energy universe, where all existence balances perfectly on the edge of nothingness. These aren't just wild guesses, they're rigorous attempts to solve paradoxes that defy classical physics, born from the collision of quantum mechanics and relativity. What makes these ideas so electrifying isn't just their strangeness, but their testability. The James Webb Space Telescope might soon spot anomalies in early galaxy formation that hint at cosmic inflation's rivals, like the ekpyrotic universe's colliding brains. Quantum gravity experiments could uncover evidence of spacetime's pixelated nature, backing loop quantum gravity's vision of a bouncing cosmos. Even the simulation hypothesis, often dismissed as philosophy, could face scrutiny if physicists detect mathematical artifacts in particle collisions, glitches in reality's code. The line between sci-fi and science has never been thinner, and we're living in the era where it might finally blur for good. But here's the real wonder: these theories aren't just about answers. They're about questions, about daring to ask what if in ways that unsettle and exhilarate. Whether it's the Fermi paradox's silence pointing to a simulated cosmos or dark flow's pull suggesting a multiverse beyond our horizon, each mystery invites us to rethink our place in the grand scheme. The universe doesn't owe us clarity. It's our job to keep probing, doubting, and marveling at the puzzles it leaves behind. So stay curious. The next breakthrough might lurk in data from a telescope not yet built or scribbled on a theorist's chalkboard tomorrow. Until then, the cosmos remains the greatest story ever told, one we're all writing together, one observation at a time. If these mysteries lit a spark, hit subscribe. We're just getting started, and the universe has plenty more secrets to share.